Hello everyone, welcome to our discussion of section 8.2 where we will be talking about series. Now we've already talked about sequences, which is a series, a set of numbers with some kind of a pattern in them. Now series, generally speaking, is simply, series are simply adding the terms in a sequence. We call that the result is a series. So we begin, as you can see on the screen, with the general notation for an infinite sequence. That's generally what they look like, an infinite sequence. And adding the terms in an infinite sequence gives us a series, simply summing up the terms. Now here's an example. For example, we have pi, which is an irrational number with infinitely many terms in that number. The partial series for pi can be written as what you see on the screen. So each digit plus the other digit written in a fraction form, such that each fraction, if you continue looking at this, you'll see a pattern, at least in the denominator of these fractions. So right in this basic example, you can see the main reason why we study series. Especially this has many applications in advanced mathematics. Many of you who might take Calculus 2 just as the last math class, you won't probably see many applications of series. But if you continue with advanced mathematics, you'll see that series are often used to solve very complicated equations. So in such equations, just like this, suppose a complicated equation has a solution equal to pi. Now, a series can be used in connection with the function that it's representing. It can be used to model this or approximate this solution. That's why we care a lot about whether series converge or not. Because if they converge to the solution of the complicated equation we're trying to model using a series. We will, in this section and in the upcoming sections, we will talk extensively about when a series converges and when it diverges. So convergence of a series is pretty important in many cases because of the way series model solutions of complicated equations otherwise that otherwise we could not solve. So people ask me, well, okay, fine, series converge and diverge. These are the techniques to establish that, but why do we care whether series converge or not? And here is this basic example just demonstrates that. Okay, so for a partial sum, one thing we will make use of to calculate the value that a series might converge or not is to make use of a partial sum. Now, partial sum have this notation, this basic notation, and we use them because it's impossible to add infinitely many terms. So if n is approaching infinity, there's no way for us to add all these infinitely many terms. So instead we use this partial sum, which can be represented with this notation or this notation. So if you see either of these two notations, we're referring to the partial sum. So the definition of a convergent series is that given an infinite series, such as that, we can compute its partial sum, denoted by S of n, as that, only if the sequence is convergent. So if the sequence is divergent, which is what we studied in the previous section, 8.1, when the sequences are divergent and when they're convergent, if the sequence is divergent, then there's no point to calculating the partial sum because we know that the partial sums will diverge as well. But if the sequence is convergent, and so this and is pretty important given these two conditions at the same time, that the sequences converge, that the sequence is convergent, and the partial sum exists as a real number. So when we calculate the partial sum, it must equal to some real number based on the fact that also the sequence that it's based on, the sequence is also convergent, and we have a real number limit for the partial sum, then we can say that the series is convergent. So if the sequence is divergent, then the series is divergent. Remember, the series is just the summation of the terms in an infinite sequence. Now, to establish this piece, to establish this calculation, whether a sequence is convergent and to come up with the limit of a partial sum, partial fraction decomposition may be necessary to show this. So sometimes, not always, just remember that we've already studied partial fraction in the previous chapter, and we will make use of it here when necessary in order to establish whether, the partial sum for a series. Okay, so that's just coming up. In some of the examples, you'll see that. So here's a couple of notes. First one, the sum of series is the limit of the sequence of partial sums. So the sum of the series is basically the limit of the sequence of partial sums. Okay, this is just the notation for that. And we studied in Calculus 1 that 0 to 0 power is a case where we will need to use the L'Hopital rule if the limit ends up being 0 to 0 power. That was in Calculus 1. But when we deal with series, the convention is that x to 0 is equal to 1 even when x, or the base number, is equal to 0. So this is one of those exceptions. In Calculus 1, when we were calculating the limits, we learned that we will have to use the L'Hopital rule if the limit of a function ends up being 0 to 0 power. That was one of the nearly 10 indeterminate cases that we looked at in Calculus 1. But here, for series, 0 to 0 power also equals 1. Okay, just remember that. So one of the more useful geometric sequences and series is the geometric sequences and series. Basically, they have this form. So this is a geometric sequence with a coefficient. This coefficient could be 1, in which case you don't see it written. Instead, you'll see, if it's 1, you'll see some number raised to some power n, or n minus 1, either way, but some power. Now, an is the nth term in the sequence, in the geometric sequence, maybe I should have said. K is any real number. R is called the common ratio obtained as any among two consecutive numbers in the sequence. If you divide a number by the number previous to it in that sequence, you will get the common ratio, which is R. And this number is always constant. I'm pretty sure when you remember this from Pre-Calculus 1 or Math 126 if you took it here. So this number R is always a constant value for a single geometric sequence. So maybe I should make a note of it, that this is always a constant value in a geometric sequence. In other words, it doesn't matter what pairs of numbers you pick, what consecutive pairs of numbers you pick in a sequence, the common ratio is always going to be the same. The n, then, of course, is the order number within the sequence. So whether it's the fifth number that you're trying to calculate, so n would be 5. If it's the 10th number you're looking for in this geometric sequence, n would be 10, and so on and so forth. Now, given a geometric sequence, then the geometric series has this kind of has this formula for its partial sum. And this partial sum applies to any number of digits within the series. So if you're adding 50 numbers, then you could apply this. So n would be 50. If you're adding up 100 digits within this series, then this would be 100, and so on. And a here is the first. This is very, very important, and it's caused confusion before. I've seen this. A is the first term in the series, or you can call it the first term in the sequence. But it's the first digit in the sequence or the series that is A. And then times this quantity divided by 1 minus r. Now, when n goes to infinity, so this is the partial sum for any number of digits. But when that n, that power goes to infinity, then the formula, the partial sum formula for the geometric series becomes a, or the first number in the series, divided by 1 minus r. So it simplifies that if we're taking the partial sum over the entire infinite series. Okay, so this is the same formula, but with the exception that n is infinity here, and it leads to that. So very, very important. If the common ratio, which we termed as r up here, that constant value that results from dividing any number in the sequence or series by the number before it, if the absolute value of that number is less than 1, then the geometric series converges. If the absolute value of r is greater than or equal to 1, the geometric series diverges. This is a really nice, convenient way of determining whether a geometric series converges or not before we start looking for its limit or its partial sum. So it saves us time. We already know whether the geometric series diverges or converges. In this theorem, these are, I'm sure you'll notice that these are very, very intuitive. You don't need to remember much about this. It's just saying that if you have two convergent series, then so are the series that are the result of some kind of operation between these two convergent series. So these operations are, one is that when we multiply one of the convergent series, this one, by a constant, the resultant is also a converging series. If we add these two convergent series, the result is a series that is also convergent. If we subtract those two converging series, the result is a series that is also convergent. So then this we can, and again, this is intuitive too. The series of the infinite series of the sum of two sequences is the sum of the individual infinite series. And the same thing applies to the difference between those two converging series. Okay. So this is very, very convenient way, and as you can see in the examples that are coming up, that says that if the series is convergent, we automatically can say that the limit of the series is equal to 0 as n goes to infinity. So if we have a series that is convergent, then the limit of the sequence as n goes to infinity must be equal to 0. But the important thing is, right away we should mention that the converse of this is not true. Even though it would be convenient to think that way, but it's not true. We can't conclude the other way around. So we can't say that if we find that the limit of a sequence as n goes to infinity equals 0, then series must be convergent. No, we cannot turn this theorem around going the other way. The converse of this theorem is not true. It's just that we know that if a series is convergent, then we must have the limit of the sequence as n goes to infinity must be equal to 0. And this is just saying that the converse is not true. So the test for divergence is another way, convenient way, to figure out if a series is convergent or divergent. So we say that the limit of a sequence as n goes to infinity, if that limit does not exist, or if that limit is not equal to 0, then the original series is divergent. This is again very, very important. So if the limit of the sequence does not exist, in other words, if it's equal to infinity, which is the same thing as saying that the limit of the sequence does not exist, or if the limit of the sequence is some value, let's say 5, which is not equal to 0, then the series is divergent. So the limit of the sequence can exist. If it's not equal to 0, then the series is divergent. So referring back to this, maybe I can put all this on the screen as much as I possibly can. So this note, it refers to the test for divergence. Referring back to the test for divergence above, in other words, we are saying that if the limit of the sequence as n goes to infinity is not equal to 0, then the series is divergent. Again, if this limit is equal to, say, 4, 2, 1/2, something that is not equal to 0, then the series is divergent. If it's equal to 0, we know nothing about the convergence or divergence of the series. So we have to use some other test to establish that. Okay, this page 5, we had some really useful theorems, or tests for divergence. So please make sure that you remember these as we tackle the upcoming examples. Okay, so here we want to, in this case, they are telling us that we have a geometric series. So that's established. Sometimes this is not always known. We have to establish what kind of series we have. But in this case, we don't have to worry about it. We know that in these few upcoming examples, we have geometric series. So determine whether the geometric series is convergent or divergent. And we know how to establish that, right? If I bring this back, it depends on whether a geometric series converges or diverges, depends on the absolute value of R. If the absolute value of R, and I'm looking for this slide here on the bottom of page 3, if the absolute value of R is less than 1, the geometric series converges. If the absolute value of R is greater than or equal to 1, the geometric series diverges. So the first thing we want to establish in this example is what is the value of R. And as we mentioned on the same page, the value of R can be obtained by taking the ratio of any pair of number in this series, any consecutive pair, by dividing the next number, or 0.5, by the previous number to it. So if you do that, you'll see that the ratio is 1/4. You can do that between this pair. So divide 0.125 by the number previous to it. And again, don't take my word for it. Calculate it using your calculator. This is again 0.25 or 1 over 4. You can do it for this pair. So 0.03125 divided by that number, and you'll see that you'll get 0.25 or 1 over 4. So R, we established, is equal to 1 over 4. Now, based on that, note that because absolute value of R is equal to absolute value of 1 over 4, and it's less than 1, right? So we can conclude that the series converges. Okay, so this is one of the things that they asked us to establish, whether the geometric series is convergent or divergent. And then if it's convergent, they say, find its sum. So how do we find the sum of an infinite geometric series? We have this formula, right? If I can find it quickly. The sum of the partial sum of an infinite geometric series, and this is coming again from page 3 where we talked about geometric sequences and series, has this formula: A divided by 1 minus R, A being the first term in the series. Okay, this is our formula. So let's apply it. So the partial sum is equal to A for a geometric series, right? Sorry, let me move this up a little bit. A divided by 1 minus R. A being the first number in the sequence, which is 2, right? So 2 divided by 1 minus the common ratio 1 over 4. Of course, this is 2. 1 minus 1 over 4 is 3 over 4. And of course, when we simplify this complex fraction, we get 8 over 3. So the series converges, and it converges to this sum. Again, series, I keep going back to why we study whether series converge or diverge. So series can be used to model the solution of complicated equations. So in such case, for example, we could arrive at that solution for a particular equation model. There are many other applications in computer science too, but most applications of series are in advanced level. So if you never study that, you'll never see those applications. Okay, so this one, again, we know that we have a geometric series here. So let's find out what the common ratio is, because they're asking us to determine whether this is convergent or divergent. So I'm going to then try to find the R here. So notice that this denominator, we can simplify this. So let me rewrite that. So we have that, and I'm going to 3 to 1 power, it's just 1/3, right? So I can write this as pi to n power divided by, let's break up this denominator. So we have 3 times 3 to n power. It's the same thing as that. 3 to n plus 1 power, right? And then, of course, this is just 1/3. We can bring that constant value and put it in front of the series. So we have 1/3 times the infinite series, and then we have pi to the n divided by 3 to the n. And of course we can yet simplify this again by writing 1/3 times the series pi over 3 to n power, right? Just rewriting that. Now we can establish, or we can say what r is. R, in this case, is pi over 3. Note that absolute value of r is absolute value of pi over 3. And of course, pi is greater than 3, 3.14 something. And so this ratio is definitely larger than 1. And we know that if the absolute value of common ratio is greater than 1, we have a divergent geometric series. So we can write that the series, or the geometric series, is divergent. So we don't need to look for its sum. Okay, the series is divergent and it has no sum. Thus, it has no sum. Okay. In our next example, again, we are told that this is part of the same set of examples, so we know this is a geometric series. And if we're after to establish whether this is convergent or divergent, let's find the r. So please pause the video at this point and see. You should be able to, after those couple examples, you should be able to easily figure out whether this is convergent or divergent. And if it is convergent, what is its sum? We discussed all those formulas and methods so far. So please pause and then come back to this. Okay, hopefully you've done that and my solution agrees with your solution, which would be great. So the first thing I would do is just write this in a way that it makes it obvious for me what the r is. So I will write it like this, put the n on the outside. So now this, easily we can see that this is r. Absolute value of r is equal to absolute value of 1 over square root of 2. And this is, square root of 2 is some 1.4 something, so definitely this ratio is less than 1. So we can say that the series is convergent. Right? That's one thing they wanted us to determine. And so now that we've established that, we need to find its sum. So what would be the first term? We know that the partial sum is for the infinite sum is a over 1 minus r. So a would be, a is when n equals 0, right? The a is the first term in the series. And notice the n doesn't start from 1. So you can say that the a is 1 over square root of 2. Notice the n starts with 0. So the first term would be 1 over square root of 2 to 0 power. So that's pretty important, that n start from 0, not 1. So therefore, the first term in the series is 1. R, we already established it's 1 over square root of 2. So now we can plug in and figure out the sum, or the partial sum, for this infinite geometric series. So we have S of n equals 1 divided by 1 minus r, which is 1 over a square root of 2. Okay, so this is a complex fraction. We need to simplify it. And so what do we have? We have S of n equals 1. If we take the common denominator here, we will end up with square root of 2 and square root of 2 minus 1. And that will result in, let me move this up a little bit. that will result in square root of 2 over square root of 2 minus 1. So of course, we want to rationalize the denominator here. So let's multiply this by square root of 2 plus 1 over square root of 2 plus 1. And let me make a note of that we are rationalizing the denominator here. And what do we get? We get, so we have square root of 2 times square root of 2 plus 1 in the numerator. In the denominator, we have 2 minus 1. Right? So that's just 1, and we end up with square root of 2 times square root of 2 plus 1. And then let's distribute that. We get 2 plus square root of 2. So that is the sum to which our geometric series converges. Okay. Okay, so let's see. In the next example, so now we have, they're asking us to determine if the series is convergent or divergent. These, from this point forward, the geometric series may be mixed in with other series. So we don't know unless we establish that. Or they could be just some other series. Okay, but these are some series, and we still have to determine whether they're convergent or divergent, and if they're divergent, then we have to determine their sum. Okay, so from back in, I guess it was calculus 1 for sure, but maybe even pre-calculus 1, when we in calculus 1, when we established the limits of rational fractions, we divided every term by the highest variable power term, the variable term with the highest power in the denominator. We divided every term in the rational expression by that. Okay, so let's do that again. So I'll just start by, so use that hint to do your own work on a piece of scratch paper in the next 10 minutes and see how far you can take this with that hint that I just gave, and then come back to the video with your own solution already done. So then if we take k as k approaches infinity, that would be equal to the limit of this series. And I'm going to distribute these in a second. So k times k plus 2 over k plus 3 squared. So let's expand everything here. We have limit as k goes to infinity. Distribute this. We get k squared plus 2k. And expanding this, we get k squared plus 6k plus 9. And then let's divide every term in this rational expression by the variable term with the highest power that appears in the denominator. That would be k squared. So we will have, right here, we would have the limit as k approaches infinity of k squared over k squared plus 2k over k squared divided by k squared over k squared plus 6k over k squared plus 9 over k squared. Okay. Now if we simplify, what will we get? So we get limit as k goes to infinity. That would be simplified to just 1 plus 2 over k. divided by, this would be just 1 plus 6 over k plus 9 over k squared. Okay, and then let's apply the limit. What will we get? This term reduces to 0. 1 plus this term will be 0, and so is that one will be 0. And this will reduce to 1. So this is limit of that. I guess we can call limit of the s of k as k goes to infinity is equal to 1. So we have something that is not equal to 0. And we had a theorem that says that, and I guess maybe I can quickly bring it back to remind you of it, if I can find it very quickly. See this one on page 5? If the limit does not exist, or if the limit is not equal to 0, right? For sure, then the series is divergent. So for sure, and maybe I should say not, so to correct my notation, I should say that is equal to that, and so, which is not equal to 0. Okay? So because of that, and this is by the test for divergence on page 5 of these notes, the series diverges. Okay, like that. All right, so let's look at another example of the same type. So here we have another series. And we want to know if it diverges or converges. And if it converges, we'll have to find its sum. So go ahead, pause this. And this is a short one, so see if it shouldn't take you more than 5 minutes to figure out if this diverges or converges. Okay, I'm hoping that you've done that. So this let's set this equal to some sequence a sub n cosine of 1 over n. So let's take the limit of this sequence, just like the previous example. As n goes to infinity, cosine of 1 over n. Of course, as n goes to infinity, this term in the argument of the cosine function becomes 0. So we know cosine of 0 from trigonometry is equal to 1, right? So notice once again that limit of the sequence as n goes to infinity is something that is not equal to 0. It's equal to 1. So thus, limit of the sequence as n goes to infinity is not equal to 0. So once again, by the test for divergence, the series diverges. Okay, so you'll see how useful this is, the test for divergence is. Okay. In the next example, so we can, using the properties or the theorem that we saw before in the previous sheets, we can break this up, right, into, this is the infinite series of the difference between some terms. We can break this up into individual series of this minus infinite series of that, with n beginning at 1. Okay, so let's do that. So let's break this up to n from the infinite series from 1 to infinity of 0.8 to n minus 1 minus infinite series from 1 to infinity of this quantity. So we have 0.3 to n. So both of these are some quantity raised to some power n, so they are both geometric series, right? So let's make a note of that. Note that both are geometric series with, of course, 0.8 and 0.3, both of them are the common ratios that are less than 1, with absolute value of r less than 1. Right? Absolute value of 0.8 is less than 1. Absolute value of 0.3 is less than 1. So both of these geometric series converge. Therefore, the difference between two converging geometric series also converges, right? So are convergent. So the difference between them is also convergent. So all we have to do is find the sum of that, and we know how to do that. We'll just apply the partial sum formula for the geometric series to each one individually. So for this one, so we have this equals 1. So in each one, if we start the n from 1, what would be the first term for this? It would be 1, right? So for, well, maybe I should make a note of that here. So let me do that. So for n minus 1, a is equal to 1. For the other one, a would be 0.3, right? The first term in the series. Just substitute for n with 1 here, substitute for n with 1 here, and you'll get the a for each one. So then, for this one, we'd have the first term in the series 1 divided by 1 minus r, which would be 0.8. And then we have subtraction here, right? So minus the first term for this series, which is 0.3, divided by 1 minus the common ratio for that series, which is 0.3. Okay, so we have, let's move this up a little bit. So we have 1 over 0.2 minus 0.3 divided by 0.7. So this is simply 5, right? If you calculate this, so this is 5 minus, this is 3 over 7. If we simplify it, this would be 3 over 7. Therefore, so S of n is, after taking the common denominator, that would be 35 minus 3, or 32 over 7. So this is the sum, or the partial sum of the series. In this example, so we are given a series. This time we are given individual terms. So we have to detect some kind of a pattern and see what we can do with this. So notice that the alternating terms start with numerator 1, and then in between we have 2, 2, 2. Right? So let's combine the terms that have 1 as the numerator. So we can rewrite this series as this. We can say this is 1 over 3, kind of change the order, plus 1 over 27 plus 1 over 243 plus, oh, of course, this is infinite, so I should put dot, 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 and then my parentheses. I will fix this. I will clean this up before posting this on Canvas, these lecture notes. And for the other one, then we have 2 over 9 plus 2 over 81 plus 2 over 729 plus dot, dot, dot again. Right? We can rewrite this series like that. Then notice that this piece, so notice that each one is actually a geometric series. This is 1/3, and then this is 1/3 cubed, right? And this is 1/3 to some other power. Let's see. So this would be so 243 divided by 27. Let's see, 1, 2, and I guess it would be 12. So some factor of 3. Let me see I grab my calculator here. So it should be some factor of 3. And we have 243 divided by 27, so 9. Right. So we have here a geometric series. If we divide each pair, so divide 1 over 243 divided by 1 over 27, you'll get the same ratio as you get by dividing 1 over 27 by 1/3. That's a good way of establishing that we have a geometric series here. Okay, so if we divide 1 over 27, and this would be r, divided by 1 over 3, we'll get 3 over 27, which is 1 over 9. If we do the same thing on this side, we get, by the way, you'll get 1 over 9. I just calculated this divided by this term, you get 1 over 9 again. So here, if we divide 2 over 81 by 2 over 9, the 2's cancel, 9 over 81 cancels to 1 over 9 again. And you will get the same thing by dividing this by that. Okay, so both are geometric series. Let me move this up a little bit. Both series with absolute value of r equals absolute value of 1 over 9, which is less than 1, right? So this is, so they converge. So the whole thing converges. So the sum, and they converge. So both pieces, so the series converges. And I'll put an arrow here, thus is convergent. And of course, we'll have to find the sum of this, the partial sum. We already know that the first term is 1/3, right? The first term is 1/3. The common ratio is 1 over 9. So we have everything we need here. So thus we have the partial sum would be equal to, a over 1 minus r, which would be 1 over 3 divided by 1 minus 1 over 9. And so we have, what do we have here? We have 9, that would be 8 over 9. And so this would be 9 over 3 times 8. And of course this would be 3 over 8. Okay, so this would be, since we divide, so this would be the partial sum for this one. So let me simplify this. So this would be 3 over 8. And this is I guess, I don't know if I can fit everything on the screen, but this partial sum we calculated is for this portion of the series that has this pattern with 1 in the numerator and multiples of 9 in the denominator. For this piece, though, then we'll calculate another partial sum with the first term as 2 over 9. So I want to make sure that I include that. So this piece is for this portion, 1/3 plus 1 over 27 plus 1 over 243 plus ... So that's for that. Now, for the other piece, so this breaking up the series into different parts, here and here, is another technique we can use. Notice that that's what we did here too, but we had a different notation. Yet we broke up the series into individual series like that. And here we're doing the same thing in a different way, right? So, and then let me make sure that I connect this. So 2 over 9 plus 2 over 81 plus 2 over 729 plus ... And that, for this part of the series, the partial sum would be such that the first term would be 2 over 9, not 1 over 3, right? So 2 over 9 divided by 1 minus, again, 1 over 9. And then, let's see, so we have 2 over 9 and 8 over 9. And so the 9's cancel, we get 1/4, right? So we get 1 over 4. Okay, so let's add those. So the original sum, let me the original series converges to, and let me make a correction here where it says thus the series is convergent. I should say the series are convergent, right? Are, since we broke this up into two segments. So the series are convergent. So the original series converges to sum of these two, 3 over 8 plus 1 over 4. And we have this, or 5 over 8. Okay. Like that. So in this example, we are changing gears to something called the telescoping sums. And I've given a quick definition of it here on the screen. Determine whether the series is convergent or divergent by expressing the partial sum as a telescoping sum. So note, telescoping sums are finite sums so they're finite sums. That's pretty important. Let me actually underline that. So this will be finite sums where most terms cancel each other with the exception of the initial and some of the final terms. So this is always present. So initial term, as far as I remember and I've seen, the initial term usually doesn't cancel, usually. And I say that with a caution that there might be one that even the initial one cancels, but I don't think so. The initial term is always present and some of the final terms. So this will vary from telescoping sum to telescoping sum. This will vary. Sometimes the last 2 or 3 terms don't cancel out. Sometimes just the very last term and the very initial terms don't cancel, and everything in between cancels. But to generalize this, the telescoping sums are such that most of the terms cancel each other out. So you have plus 1 over 4, minus 1 over 4, and they cancel each other out like that, with the exception of the initial and usually some of the final terms. Just remember that definition for telescoping sums. Okay, so, and then if the series is convergent, then find its sum. So let's do that. So the first thing, this, by the way, it suggests when we're talking about the initial and some of the final terms, generally speaking, when you see this telescoping sum mentioned, then it means you should write out several of the beginning terms and some of the final terms. So let's do that. We always have to do that for telescoping sums. So calculating, and I'll make a mention of that here. For all telescoping sums, we will need to list some of the beginning and some of the final terms in the series. So if we do that for this, and we'll use n equals 1 to begin with. So we'll say the partial sum would be equal to natural log of plug in for n with 1, we get 1 over 2, right? That's just for n equals 1. And then for n equals 2 And I'll just do a few in the beginning and the very last one. So for n equals 2, we get natural log of 2 over 3. For n equals 3, we get natural log of 3 over 4, and so on and so forth. And the last one will be that, right? The last one where n equals n will get just that. So natural log of n divided by n plus 1. For all telescoping sums, we'll have to do this. Now, so how do we cancel this? Let's remember some of the log properties that we learned in beginning algebra, classes like Math 124, Math 126, that we can rewrite each term in, because these are ratios, we can write them as difference of natural log terms, right? So we can, doing that, we will get, for this term, we will get natural log of 1 minus natural log of 2 plus natural log of 2 minus natural log of 3 plus natural log of 2 minus, natural log of 3, that's coming from this, minus natural log of 4. And then plus natural log of, if I can fit it here, natural log of n minus natural log of n plus 1. I could barely fit it there. So now if you look at the expansion of this partial sum, let's see what terms cancel out. So the initial term didn't cancel, right? But minus natural log of 2 and plus natural log of 2, they cancel out. Minus natural log of 3 and plus natural log of 3 cancel out, and so on. So it looks like, just looking at the pattern of cancellation in the beginning terms, you'll see that the next one will cancel minus natural log of 4. So, and then natural log of n will also cancel. So the only ones that are going to remain at the end will be, it'll be, the partial sum will equal to natural log of 1, which by the way is 0, and minus that last term. And I'm saying this just looking at the pattern of cancellation in the middle. Minus natural log of n plus 1. So even that will cancel. Okay? So even that will cancel with the previous term. So now, and notice that this is a finite sum, right? So this is why we said that this is a finite sum. So it ends at that point. And then, so looking at this, what do we have? We have this, which will be 0, equal to 0. And then we have what we have left with, then let's take the limit of that. So limit of the partial sum as n goes to infinity would be equal to limit of this term, right? So minus natural log of n plus 1 as n goes to infinity. So of course, if you plug in for n with infinity, that will be natural log of infinity. So minus that, it would be very large negative number. So, or minus infinity to be exact. So minus infinity. So we can say that this series is divergent. Right? So because of that, the series is divergent. So no need to look for its sum, right? It won't have any sum. So let's look at another example of this. For telescope. So this is again part of that example. And because we know this is a telescope, it will have it will have a partial sum which is a telescoping sum, then let's list some of the first and the last terms of this partial sum. So once again, but I will make a note of that. And because you've seen one example already, please take the time to pause the video right now and spend no more than 15 or 20 minutes, definitely no more than 20 minutes, and solve this on your own. See if it's divergent or convergent, and hopefully our answers agree. So once again, calculating the first and the last terms for the partial sum. So what do we have? We'll start with n equals 1 again and list those terms. So the partial sum will be equal to e to 1 and then minus, and I will put that in parentheses, minus e to 1 over 2. And then plus, for n equals 2, we'll get e to 1/2 minus e to 1 over 3 plus, for n equals 3, and I'll stop there, and maybe also the last term, I'll do that. So 1e to 1/3 power minus e to 1 over 4, and then plus, maybe I can fit that, hopefully. And then the last term would be that, right? So e to 1n power minus e to 1 over n plus 1 power. And barely it fit. Okay, so once again, let's see how the terms cancel in this telescoping sum. So again, the first term is just e, it won't cancel, right? But this one and that one add up to 0. Notice this one and that one add up to 0. These two examples turn out to be like this, where the consecutive terms cancel out except the first and the last term. But this is not always the case. Sometimes you'll have this term staying, and this term staying, and maybe this term, and then these start canceling. So be aware of that. So you have to list several of the beginning terms and several of the last terms to see how the cancellation pattern is happening within the sum. So looking at this pattern, then I'm sure we will also cancel this, and this one will cancel too, so we will end up with only the first and the last term in this telescoping sum, right? So let's write this out. So this would be e simply, and then e, and that would be minus e to 1 over n plus 1. Okay. And then now we can take the original series, let's, so I'm going to bring that down again, write this down again. So that is equal to the limit of this partial sum, right? Limit of the partial sum as n goes to infinity, which means this would be equal to the limit as n goes to infinity of that quantity, e minus e to 1 over n plus 1 power. Okay, so of course, if you take the limit of this quantity, then the power here will be 0, right? 1 over infinity would be 0, e to 0 would be 1. So we'll end up with e minus 1. So that is what we that is what our series converges to. Converges to E minus 1. Okay, so this is another example of this type. When we'll work on class worksheet, then you'll see other types of telescoping sums that where the terms don't actually cancel like this. So this one will stay, that one will stay, that one and that one will cancel. So you'll have to keep all the terms. The point I'm making is that you have to keep all the terms that are not canceling within this partial sum, and then take the limit of it as n goes to infinity. Okay, so this is a different type of example. I thought maybe to include one of these at least. It's not too bad if we see an example of this type. Usually these type of examples take several pages of solving them, but this isn't too bad. So I thought it's nice to include at least one of these, and we'll do one in class when we work on the worksheet for this section. So it's saying that find values of x for which the series converges. Find the sum of the series for those values of x. So we have to determine, given this series, we have to determine values of x for which this will converge. Okay, we have to leave out any x term for which this series would diverge. Okay, the first thing is notice that the power of -4 and the power of this binomial are equal. They're both n. So let's combine this whole thing into one. So let's do that. We will have n going from 0 to infinity of -4 times x minus 5 to n power. Does this look familiar? It should, right? So this quantity to some n power, this is a geometric series. So let me note that this is a geometric series. And what do we know about geometric series? We know that if this is geometric series, so this is R, right? So this would be the common ratio for this geometric series. And for that series to converge, that ratio must be, the absolute value of that R, common ratio, must be less than 1. So make a note of that, and thus we must satisfy this inequality, that absolute value of that. So this is the R, right? Absolute value of, I'll just write it here actually. R is equal to -4 times x minus 5. Therefore, absolute value of R equals absolute value of -4 times x minus 5 must be less than 1. Okay, we must satisfy this inequality. Well, let's solve this simple inequality and go from there. So in other words, and I'll start from here to save space. In other words, we'll have, looking at that, absolute value of -4 times absolute value of x minus 5 must be less than 1. Now that would be just 4, positive 4, right? So we can rewrite this as absolute value of x minus 5 less than 1 over 4, which means then we can rewrite this as, this is basic algebra now, as I'm sure you remember. X minus 5 is greater than minus 1 over 4 and less than 1 over 4, right? So then let's go from this, then add 5 to all sides. What do we get? We get 5 minus 1 over 4. In the middle, we just get x, and then 5 plus 1 over 4. And then we have here common denominator. This would be 20 minus 1, or 19 over 4. And here we get 20 plus 1, 21 over 4. Right? So this is, if we are to make sure that this series converges, we must restrict this x to these values, to this interval, to this open interval, right? Not including 19 over 4 and not including 21 over 4. So let me just say that. The series will converge. I should have said the geometric series. The geometric series will converge when x is restricted to this interval. Okay. All right. So now that we know that, then they say, find the sum. Right? So we established that. We now know for what values of x this series will converge. Then they say, find the sum of the series for those values of x. So I will write that here. Maybe I should put an arrow like that. Okay, so we know that for a geometric series, the partial sum is a over 1 minus r. And in this case, so a would be 1, right? So because n starts at 0, and if you plug in for n with 0, you'll get 1 here times 1 here. So the first term in the series with its n set as 0 is equal to 1. 1 over 1 minus, of course, we established this is r. This is r, right? So 1 minus 4 times x minus 5. That is the r for us in this case, with x restricted to this, right? For this sum formula to yield a correct result for us, to yield a correct partial sum result for us. Okay, so let's simplify this. What do we get? We get the partial sum is equal to 1 over 1 minus, so we have minus 4x, right? Distributing that, plus 20. And then minus 20 plus 1, that would be minus 19. So we get 1 over, and then plus 4x. So 4x minus 19. Okay, so given this series, the geometric series will converge to this quantity, to this partial sum, when x is between 19 over 4 and 21 over 4. So this is the That's our final sum restricted to these x values. Okay, so this wraps up section 8.2. I hope it was worth your time and it helps you better understand the topics in this section. And I thank you for watching this video until the end. For now, have a nice day, and I'll see you again next time.